So I had section 2 of chapter 16, which talks about the analysis of variance. The section I had starts off with the details of the various estimates. So the analysis of variance uses sample variance estimates to measure variability between and within groups. Sample variance measures variability among any set of observations by first finding the sum of squares, which is here, and then dividing the sum of squares by degrees of freedom, which is right here. So sample variance can be used to identify two general features for each of the several variance estimates in ANOVA. One is the sum of squares in the numerator. The numerator term of any variance estimate is the sum of squares. And then for the second one, the degrees of freedom in the denominator, the degrees of any variance estimate is degrees of freedom in NAOVA. So the mean square, a variance estimate in ANOVA, referred to as a mean square, consists of the sum of the squares divided by its degrees of freedom, which is what we just went over. So it's MS equals SS divided by DS. Then we go into the sum of squares definitional formula. So the sum of squares is the sum of squared deviations from some set of scores about their mean. And there's three terms that can be used. So the first one is SS total, and that equals the summation of x minus the mean grand squared. So although not directly involved with the calculation of the F ratio, it serves as a valuable computational check. The SS between equals the number of scores in each group times the summation of the population mean of the group minus the population mean of grand squared. This contributes to the numerator of F ratio. The sample size for each group, which is n, reflects the fact that deviation is the mean group minus mean grand is the same for every score in that group. And then the last one is SS within, which equals the summation of x minus the mean group squared, and this contributes to the denominator of the F ratio and always reflects only the pooled variability among subjects treated similarly, can be referred to as the sum of squares for random error or SS error. So sum of squares computational formulas. It's more efficient as well as accurate to use equivalent computational formulas to calculate the various SS terms that's present here. There are some common features of the original computational formula and the new computation formulas. So each formula consists of two components separated by a minus sign. The means are replaced by their corresponding totals, and whether a score or a total, each entry in the numerator is squared, and in the case of a total, divided by its sample size, either n for the grand total or small n for any group total. So you can refer to tables 16.2 and 16.3 for this information. So checking computational accuracy. To minimize computational errors, you can calculate the three SS terms from scratch and then do the sum of squares one factor to double check yourself. So it would be SS total equals SS between plus SS within. Degrees of freedom. So just a reminder, degrees of freedom refers to the number of deviations free to vary in any sum of squares term, given one or more restrictions. The restriction always entails the loss of 1 degree of freedom because the sum must equal 0 for each set of deviations about its respective mean. And then you look at table 16.4. So n minus 1 degrees of freedom for df total reflects the loss of 1 degree of freedom when all n scores are expressed as deviations around their grand mean. K minus 1 degrees of freedom for df between reflects the loss of 1 degree of freedom when the k group means are expressed as deviations about the 1 grand mean. And then n minus k degrees of freedom for df within reflect the loss of 1 degree of freedom when each subset of the n scores is expressed as deviations about their respective group mean, or k. So to determine the degrees of freedom for any sum of squares, you just substitute the appropriate numbers and subtract. And then checking for accuracy. in NaOVA, the degrees of freedom for df total always equal the combined degrees of freedom for the remaining df terms. So the equation in this case would be df total equals df between plus df within.